Unit 7 Review. The purpose of this video is to review the topics in Unit 7. These topics are pressure vessels and combined loading. For pressure vessels, I will review both wall stress and fasteners. For combined loading, I will review the basic stress formulas, then look at how to solve problems with both three-dimensional and two-dimensional loading conditions. Lastly, I will discuss creating stress elements to represent the state of stress at a point in a structure. Use the time shown to jump to a specific topic. Pressure vessels are considered thin-walled if on any vessel cross-section the wall thickness is relatively thin compared to the internal tank radius. More precisely, the pressure vessel is thin-walled if the ratio of internal radius r divided by wall thickness T is equal to or greater than 10. Two thin-walled pressure vessel configurations are considered: cylindrical vessels and spherical vessels. At a point in the cylindrical portion of the pressure vessel, represented by the small square stress element, tensile stresses are present acting in both the hoop or circumferential direction and in the axial or longitudinal direction. Note that the hoop stress is double the axial stress. In the spherical pressure vessel, the stresses on a stress element in the tank wall are equal, regardless of the orientation of the sides of the stress element. In thin-walled pressure vessels, the radial stress acting through the thickness of the vessel wall is considered negligible. Let's consider the fasteners that are connecting the wall segments of the pressure vessels. Suppose a spherical pressure vessel has an internal pressure P. An imaginary slice is made through the bolts connecting the upper and lower sections, and a free body diagram of the upper section is shown. The forces on the section must be balanced. A force caused by the internal pressure pushes up on the top segment. The force is equal to the internal pressure acting on the circular cross-section of the free body diagram, defined by the internal radius. The upward force caused by the pressure is resisted by the individual forces in each of the bolts, shown acting downward. Note that in this configuration, each of the bolts is loaded in tension. We can write this equation based on balanced forces in the y direction. The sum of the forces in the bolts is equal to the pressure times the cross-sectional area of the tank. Since the bolts are behaving as axially loaded members, the stress equation sigma equals force divided by area applies. If the allowable normal stress in the bolts is known, the allowable tensile force on a bolt can be determined. Now consider the fasteners in the cylindrical portion of the pressure vessel shown. Slices made perpendicular to the axis of the cylinder produce the segment shown. Another slice is made through the connecting bolts, and a free body diagram of the top portion of the cylinder section is shown. Note that axial stresses and pressures have been excluded for clarity. As before, the forces on the section must be balanced. A force caused by the internal pressure pushes up on the top segment. This force is equal to the internal pressure acting on a rectangular cross-section of the free body diagram. The upward force caused by the pressure is resisted by individual forces in each of the bolts, shown acting downward. Again, note that in this configuration, each of the bolts is loaded in tension. We can write the same equation for balanced forces in the y direction. The sum of the forces in the bolts is equal to the pressure times the cross-sectional area of the slice. The bolts are axially loaded members, thus the stress equation sigma equals force divided by area applies. Note that as the length of the slice L increases, both the number of bolts in the segment and the area over which the pressure acts increase proportionally. Thus, the length of the slice is arbitrary. It is convenient to take the slice length L equal to the bolt spacing, if it is known. Here's an example pressure vessel problem. It says, the pressurized tank is made from bolting two hemispherical end caps to a cylindrical middle portion. The cylinder is composed of two half-cylinder sections bolted together. The tank has the following properties. The internal pressure is 225 psi. The wall thickness is 0.2 inches for both the end caps and the cylinder. The cylinder inner diameter is 30 inches. All bolts have a shank diameter, D, of 0.375 inches. Each end cap is attached with 20 bolts. The center-to-center spacing of the bolts in the cylinder is 2.5 inches. We are asked to determine the normal stress in the tank walls for both the cylinder and the caps at locations away from the bolted flanges. We also want to determine the normal stress in the bolts of the end caps and the cylinder. I will first solve for the stress in the tank walls. We're looking away from the bolted flanges because the presence of those flanges will likely influence the stress, but away from the flanges we just have our cylindrical and hemispherical tank walls, and we can solve for the stresses in these segments using the two equations. Sigma equals PR over T and sigma equals PR over 2T. In both equations, P is the internal pressure. R is the internal radius. Our cylinder inner diameter is 30 inches, so our inner radius is 15 inches. The same would be true for the end caps. They would need to match the cylinder, so they have an internal radius of 15 inches. The wall thickness is given as 0.2 inches for both the end caps and the cylinder. And I solve for my stress values. I'm going to show the stresses on stress elements. For the cylindrical portion of the pressure vessel, in the hoop direction, that's the circumferential direction around the cylinder, we have our largest stress, 16.9 KSI. In the axial or longitudinal direction, we have the smaller stress, 8.44 KSI. The orientation of the stress element matters. It is oriented in the same direction as the tank cylinder shown in the figure. For the end cap, the stresses are the same in all directions, and they're equal to the lower value, 8.44 KSI. The orientation of that stress element does not matter, since the stresses are the same in all directions. Now let's consider the stresses in the bolts. I'm going to begin by drawing a free body diagram of an end cap. I have sliced the end cap through the bolts that are bolting the end cap to the rest of the tank. There is a force acting on the end cap, trying to push the end cap off of the tank. That force is caused by the internal pressure. The force caused by the pressure is balanced by the forces in the 20 bolts that are holding the end cap to the tank. By summing forces in the x direction, I can write that the force caused by the pressure is equal to 20 times the force in a single bolt. Note that in a single bolt, the force on the bolt is a tension force or an axial force that is causing the bolt to experience tension. The stress equation for an axially loaded member is stress is equal to internal normal force divided by cross-sectional area. The internal normal force is the force in the bolt from our equation above. We can rewrite that equation to solve for the force in a single bolt. To find it, we will first need to find the force caused by the internal pressure. The force caused by a pressure is equal to the pressure acting over an area. Pressure times area is a force. The area is the internal area of the tank on our cross-section. In this case, it's going to be based on our inner radius. We know the pressure. It was given to us as 225 psi. Solving for the force in the bolt, it is 7,952 pounds. Now we can use our stress equation to solve for the stress in the bolt on an end cap. The area we're going to use is the area of a bolt. We were told in the problem statement that all bolts have a shank diameter of 0.375 inches. The shank of the bolt is where the bolt will feel the maximum stress. I compute that the stress in the end cap bolt is 72 KSI. Now let's find the stress in the bolts in the cylinder. We will use the same procedure, but modify it for the cylindrical portion. I'm going to cut through the cylinder so that I can create a free body diagram. The section of the cylinder that I'm going to cut is a thin section that's equal to the spacing of the bolts. I will cut halfway between two bolts on either side of one bolt. And that spacing is 2.5 inches. Here's my free body diagram. I'm only considering forces that are acting vertically. I'm ignoring the pressure component that's acting perpendicular to my slice. And I'm also ignoring the stress in the tank wall that is balancing the horizontal portion of the pressure. On my free body diagram, I have the force pushing up on the top portion of the cylinder caused by the pressure. And I have two bolts and the forces in those bolts that are reacting against the force caused by the pressure. By summing forces in the y direction, I can write this equation. The force caused by the pressure is equal to 2 times the force of a bolt. Again, we see that the forces in the bolts are tension forces. So the equation sigma equals normal force divided by area applies. The area is the cross-sectional area of the bolt, and it is the same area that was found for the bolts in the cap. The force caused by the pressure is equal to the pressure in the tank times the area on which it's acting. The area that the pressure is acting is this rectangular area of our free body diagram, shown with the hatched lines. That area is a rectangle with a width of 2.5 inches and a length equal to the inner diameter of the tank, 30 inches. Some people wonder why the area is not the curved area inside the tank. The reason is, my free body diagram cuts through the pressurized gas within the tank. So all forces are acting on the cut surface. That cut surface is through a pressurized gas, not around the inside radius of the tank. So the area the pressure is acting is a rectangular area. And I compute that the force on a single bolt in the cylinder is 8,437.5 pounds. Using the normal stress equation for an axially loaded member, I compute that the stress for the bolts in the cylindrical portion of the tank are 76.4 KSI. And now our problem is complete. We have the stress in the bolts in the cylinder, in the end cap, and the stresses in the tank wall. Let's now review the basic strength of material stress formulas. First, axially loaded members are loaded with a force in the direction of the member's primary axis. The force can be tension or compression. The internal force in the member is a normal force acting on the cross-section. The internal normal force causes normal stress on the cross-section, computed as the normal force divided by the cross-sectional area. The distribution of stress is uniform over the cross-section. Next, torsionally loaded members are loaded with a torque about the member's primary axis. The internal torque on a cross-section causes shear stress on the cross-section. The stress equation is shear stress is equal to internal torque times radial distance rho divided by the polar moment of inertia of the cross-section. Note that the distribution of shear stress on the cross-section is not uniform. It is maximum at the outside edge and zero in the very center. The direction of the stress changes over the cross-section. For members subjected to transverse loading, also known as beams, two internal reactions develop: an internal moment and an internal shear force. The moment causes normal stress on the cross-section, using the equation shown. On the neutral axis, which passes through the centroid of the cross-section, the normal stress is zero. It increases with distance from the neutral axis. On one side of the neutral axis, the surface feels compression. On the other side, it experiences tension. Which side is which depends on the direction of the moment. The internal shear force causes shear stress on the cross-section, which is calculated using the equation shown. The shear stress is typically maximum at the bending neutral axis. The shear stress magnitude is 0 at the extreme edges of the cross-section in the direction of the force, and changed parabolically in between. In pressure vessels, normal stresses develop in the plane of the pressure vessel walls, as previously discussed. In combined loading situations, a member is subjected to 2 or more of the loading conditions just considered. Combined loaded members are very common in the physical world. For example, the column of a building can be exposed to direct gravity loads, direct lateral loads, and loads from connecting members, producing a three-dimensional combined loading condition. Let's consider how to find the stress at a point in a member subjected to a three-dimensional combined loading condition, which is the general case. We will slice the member at the point of interest. The slice is always perpendicular to the member's longitudinal axis, giving the smallest possible cross-section. We then apply a coordinate system to the cross-section. Draw the coordinate system centered at the centroid of the cross-section. One axis will be normal or perpendicular to the cross-section. The other 2 axes will be oriented in the plane of the cross-section. The axes labeled as X, Y, and Z are arbitrary and can be changed. Therefore, I've labeled the axes as Q, R, and S. For three-dimensional loading, there are 6 possible internal forces and moments acting on the cross-section. There are 3 forces, 1 in each axis direction. There are 3 moments, 1 acting about each axis. The forces and moments can be found using the 6 static equilibrium equations. Some of the internal forces and moments may be 0. Let's look at just the forces. The single force perpendicular to the cross-section is a normal force and can be in tension or compression. The 2 forces parallel to the plane of the cross-section are shear forces. Their directions can be positive or negative. Now let's look at just the moments. The moment acting about the axis perpendicular to the cross-section is a torque. The 2 moments acting about the axes parallel to the plane of the cross-section are bending moments. The directions for the moments are generally defined as positive or negative using the right-hand rule, with the thumb oriented in the positive direction of the axis. Each of the 6 internal forces and moments cause stresses on the cross-section. The normal force and 2 bending moments, shown in red, cause normal stresses. The torque and 2 shear forces, shown in blue, cause shear stresses. The normal stress equations are shown. They each cause normal stress on the cross-section. In this case, tension or compression in the S-axis direction only. Since the normal stresses are all in the same direction, they combine to form some resultant S-direction normal stress state at a given point. Now, the shear stress equations are shown. They each cause shear stress on the plane of the cross-section, but in different directions: the Q direction, the R direction, or somewhere in between. Shear stresses that are acting in the same direction combine to form a net shear stress. When finding the stress at a point on the cross-section, the distribution of stress on the cross-section must be considered. As previously mentioned, normal stresses push or pull on the cross-section in the direction perpendicular to the plane of the cross-section. For the normal force, the full cross-section feels uniform stress, either tension or compression, depending on the direction of the normal force. This means all points on the cross-section experience the same normal stress contribution from the normal force. For the bending moments, tension and compression stresses are present on opposite sides of the neutral axis. The neutral axis is the axis which the moment acts about. In this case, the Q-axis is the neutral axis. And points B, C, and D all feel no stress. Also note that the moment of inertia is about the neutral axis, and the variable r is in the direction perpendicular to the neutral axis. The triangular distribution of stress, increasing with distance from the neutral axis, is depicted in the image. Use the right-hand rule to determine which side is tension and which side is compression. The fingers curl up from the tension side and swing around to push on the compression side. For this positive moment, the maximum tension stress is at point E, and the maximum compression stress is at point A. The stress distribution shown is not totally accurate. As more accurately shown here, the distribution is over the full cross-section. For the moment about the r-axis, the neutral axis is the r-axis, so points A, C, and E feel no stress. The moment of inertia axis is the r-axis, and the variable q is in the direction perpendicular to the neutral axis. By the right-hand rule, we can determine that point D feels the maximum tension stress, and point B feels the maximum compression stress for the positive moment shown. Again, the stress distribution is not totally accurate. The actual stress distribution is over the full cross-section. Let's now look at the contributions to shear stress on the cross-section. All shear stresses are acting parallel to the cross-section. For the torque, the shear stresses appear to flow around the cross-section in the same direction as the torque. At point C in the center, the shear stress is 0, since the variable rho is 0. The shear stress will be largest at the edge of the cross-section, where rho is greatest. This means that the maximum shear stress magnitude is felt equally at points A, B, E, and D. Note that the directions of the stress change for the 4 points. At point A, the stress is in the positive Q direction. At point B, the stress is in the positive R direction. At point E, the stress is in the negative Q direction. At point D, the stress is in the negative R direction. The distribution of stress magnitude is linear, increasing radially from the center outward in all directions. For the shear forces, the resulting shear stresses are distributed parabolically over the cross-section. For the circular cross-section shown, the maximum shear stress is on the axis perpendicular to the direction of the force. The force is in the q-axis direction, so the maximum stress is on the r-axis. The shear stress is uniform along any line perpendicular to the shear force, so points A, C, and E all experience the maximum stress. At the extreme edges of the cross-section in the direction of the force, the stress is 0. This is at points B and D on the cross-section. Note that the moment of inertia is about the axis perpendicular to the shear force direction, and the dimension t is measured perpendicular to the shear force direction. The direction of the stresses are in the direction of the force. For the r-axis shear force, the maximum stress occurs on the perpendicular q-axis, so points B, C, and D all experience the maximum stress. The moment of inertia axis is the q-axis, and the dimension t is measured perpendicular to the shear force direction. At the extreme edges of the cross-section, in the direction of the force, the stress is 0. This is at points A and E on the cross-section. Now we have considered all 6 forces and moments that can act on the cross-section and their resulting stress distributions. There is clearly a lot of information to keep track of. The following discussion suggests a way to organize this information. Suppose we have a combination of forces and moments acting on a cross-section, and we want to determine the stresses at points A through E. First, recognize that there are 3 possible forces and 3 possible moments that may be present. I put these 6 internal reactions as rows in a table. The approach will be to consider each force or moment and its corresponding stresses one at a time. Then, using the principle of superposition, the like stresses will be combined. I now define my axes on the cross-section. I have selected the y-axis to be perpendicular to the cross-section. The x and z-axes are then parallel to the cross-section. Now in my table I can define which force is the normal force and which forces are the shear forces. The y direction force is the normal force. It is acting in the negative y direction. The other forces, x and z directions, are shear forces, since they are parallel to the cross-section. I include a positive and negative sign to keep track of direction. There will only ever be one possible normal force and two possible shear forces. With the axes defined, I can now identify that the moment about the y-axis is the torque. The other two moments are bending moments. There will always only be one possible torque and two possible bending moments. I determine sine by the right-hand rule. The magnitudes of these forces and moments are determined using the equations of static equilibrium. Now that I have defined each force and moment, I can identify the corresponding stress equations. Note that I have adjusted the variables and subscripts to match the x, y, and z axis systems used. Note that the ordering of stress equations in the table will change if the axis system on the cross-section is changed. Now, I take one row at a time and compute stresses using the stress equation applied to each point. For the shear force in the x direction, maximum stress will be on the z-axis and will be uniform for points B, C, and D. At points A and E, the shear stress is 0. The shear stress direction is in the direction of the force, negative x. For the normal force in the y direction, the normal stress is uniform at all points. The negative sign on stresses indicates compression. For the shear force in the z direction, maximum stress will be on the x-axis and will be uniform for points A, C, and E. At points B and D, the shear stress is 0. The shear stress direction is in the direction of the force, positive z. The bending moment about the x-axis is next. The x-axis is the neutral axis, so points A, C, and E, which lie on the neutral axis, are all 0. By the right-hand rule, the moment is positive, and point D will feel the maximum tension stress, and point B will feel the maximum compression stress. The torque about the y-axis causes shear stress. Point C at the centroid will feel no shear stress. Points A, B, D, and E, which lie on the perimeter of the cross-section, will all feel the same maximum shear stress. The direction of stress at these points are in the direction of the torque, which is in the xz plane and is negative by the right-hand rule. The direction at point A is negative z. The direction at point B is negative x. The direction at point D is positive x, and the direction at point E is positive z. Last is the bending moment about the z-axis. The z-axis is the neutral axis, so points B, C, and D, which lie on the neutral axis, are all 0. By the right-hand rule, the moment is negative, and point A will feel the maximum tension stress, and point E will feel the maximum compression stress. Now, using the principle of superposition, the normal stresses at each point can be combined. The normal stresses are all acting perpendicular to the cross-section in the y direction. So they can be directly combined. Just be careful to include the sign, tension or compression. Note that points B and E will be points of maximum normal stress, since all normal stresses at each point are in the same direction. Note that at points A and D, the stresses are canceling each other out to some degree based on their magnitudes. Using the principle of superposition, the shear stresses at each point can be combined. However, they can only be combined when they are acting in the same direction. For example, for point A, the non-zero shear stresses are acting in the z direction, one positive, one negative, thus canceling each other out to some degree. At point B, the non-zero shear stresses are both acting in the negative x directions, so point B will be a point of maximum shear stress. The same is true for point E, but in the z direction. At point C, the non-zero shear stresses are acting perpendicular to each other and are thus not combined. A two-dimensional loading condition is a special case. For two-dimensional loading, all of the internal reactions can be shown on a single plane. In this case, the internal reactions reduce from 6 to 3, with two forces, typically shown in the x and y directions, and a moment acting about an axis perpendicular to the plane, typically the z-axis. The table of internal forces is reduced to match. Note that there is only one source of shear stress, but two sources of normal stress. It can be helpful to show stresses occurring at a point in a structure using a stress element. I will demonstrate this for point A from our previous example. I have drawn a three-dimensional element with the faces oriented perpendicular to the axis system in the structure. Point A is on the top surface of the free body diagram. So the top face of the stress element will correspond to the cross-section surface. We will use it as a reference surface for all the stresses. Now I will go through the stresses one at a time and show them on the stress element. The first item is the shear force in the x direction. Point A feels no shear stress from this force, so I add nothing to the element. Next is the normal force acting in the y direction. It causes compression at point A, so I show it as an arrow pointing into the top face of the element. I would also show its magnitude. The stress element must be balanced, so I add a balancing stress to the bottom of the element. Note that the stress on each face is shown with a single arrow instead of a distribution. This is typical for stress elements. Next is the shear stress caused by the shear force in the z direction. I show it on the top surface of the element, acting in the direction of the force and parallel to the surface. For the element to be balanced, a balancing stress is shown on the bottom. Additional stresses must also be present on the z-axis front and back surfaces for equilibrium. When shear stresses are present, they will always show up on four sides of the element. Note that the arrowheads on adjacent pairs of shear stresses point towards the same corner. Next is the moment about the x-axis. It causes no normal stress on the element. Next is the torque about the y-axis. It causes shear stress in the negative z direction at point A. Again, I show it on all four faces. It is, to some degree, canceling out the shear stress acting in the positive z direction. I would include the magnitudes of the stresses on the element. Last is the moment about the z-axis. It causes positive normal stress, or tension stress, at point A. The stress is normal to the cross-section, so it is acting in the y direction. I show the arrow as pointing out from the top surface of the element. A corresponding arrow is shown on the opposite side for balance. The two normal stresses are canceling each other out to some degree. Note that there are no x-direction stresses on this element. Therefore, point A is in a state of plane stress. That plane is the YZ plane. I can show the stress element as a plane element. I would compute the net normal stress and the net shear stress and show them in their correct directions on the element. This completes the review of topics that form Unit 7